Hi everyone. In this video I'm going to go over some questions from chapters 7 and 8, kind of like a practice exam, and my best guess of things you might find on the exam. So as you go through these, there's going to be several examples, including in the first couple of questions, where I quickly go over an example of a concept. But if you're not sure how to do any example, meaning you couldn't answer any ion or Lewis structure that was written in the later cases, there are two video links in the description below which will show you how to do electron configurations and will show you how to do Lewis structures. Now they are a bit long, about an hour long each, but if you spend the time in going through them, it can help you out so you can get any of these questions answered. So again, if you just know how to solve that example, that's not ideal because it's almost definitely not going to be the same example that you were going to find on an actual test. So if you want to know how to do all the examples, I strongly recommend you watch the videos in the description below. One is for electron configuration, and one is for Lewis structures. Finally, the last thing I want to mention is you can get a copy of these blank questions as well as a copy of the questions with the answers below in the description, and there are links to both of those. So that's about all I have to go over. Now I'd like to go over the first problem. Finally, also in the description below, as always, you can find links to the time so you can go over the specific question you want. All right, the first one says, give the ground state electron configuration for Br minus, bromide. So, bromine is here. Br minus is bromine with an extra electron. Said another way, it's isoelectronic or has the same electron configuration as krypton because krypton has one additional electron. Notice it's not the same because there's a different number of protons and the protons define the atom, but it does have one extra electron, so it's isoelectronic, same electron configuration as krypton. So in order to do that, we put argon in brackets. That's supposed to be a bracket. So we put argon in brackets, 4s2. These two are the s block. The d block, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember the d is one less, 3d10. So it's not the 4d, it's the 3d. And then finally, the 4p, 1, 2, 3, 4, 5, 6, because we want it to be like krypton. So 4p6. If it was bromine, it'd be 4p5, but because it's bromide, Br minus, it's 4p6. Let's do another example. And as I mentioned in the introduction, these are just two examples, but if you want to be able to do all the examples, please watch the video on electron configurations linked in the description below. Here it says give the ground state of electron configuration for Mg2+. Well, if something is 2 plus, it's missing 2 electrons. So it's not going to be like magnesium, it's going to be isoelectronic with neon. So let's count it out. 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6. So this is 1s2, 2s2, 2p6. And that is choice letter E. And I forgot on the previous one, I forgot to select the choice, but it is this electron configuration is choice letter C. So these are two electron configurations of ions. Again, there's a video down below with electron configuration if you're not sure how I just did that. Question 3 says, place the following elements in order of decreasing atomic radius. So if you'll recall, we have this trend of increasing atomic radius. And the trend is down and to the left. So francium is the biggest, helium is the smallest, and this is our order. Now let's identify the atoms. So xenon is somewhere about here. Rubidium is somewhere about here. And argon is somewhere about here. Now the other thing I suggest that you do is when you have decreasing order, ask yourself a simple question. Does this mean smallest first or biggest first? Well, if you wanted to get smaller, decreasing order, this means biggest first. So which one of these atoms is the biggest? Well, it's the one that's closest to the bottom left-hand corner. So rubidium is greater than xenon, because it's lower down than argon, is greater than argon. So using this trend and identifying the elements on the periodic table, I just used this to find them. Okay, then basically we have the trend. And here the choice is letter C. Question 4 asks, which ionization process requires the most energy? Well, ionization energy is the energy to take an electron away from something. So if we have IE1, ionization energy 1, for X in the gas phase, you get X with a positive charge in the gas phase plus an electron. Well, we could take away a second electron, IE2. If we have X plus in the gas phase, we are going to get X2 plus in the gas phase plus an electron. And we could have a third and a fourth and a fifth until all the electrons are gone in theory. But what you'll notice here is that in the IE1 case, the energy to remove a first electron, you're taking an electron away from neutral X. In this case, you're taking an electron away from X with a positive charge. It's always going to take more energy to take away an electron from X with a positive charge than from neutral X. So IE2 is always going to be greater than IE1. What about the difference between oxygen and fluorine? Well, here we have a trend on the periodic table, and this is increasing first ionization energy. So the trend is exactly the opposite of the radius trend. This time it's up and to the right. That's supposed to be a straight line, but it didn't draw it that well. So let's look at what we're looking at here. In the first case, A, this is IE1 for oxygen. Why? Because oxygen is neutral, and then we take one electron away. Now we have oxygen is plus, and we take a second electron away to get oxygen 2 plus. This is IE2 for oxygen. In this case, we have F plus and we go to F2 plus. This is IE, ionization energy 2 for fluorine. And in case D, this is ionization energy 1 for fluorine because we have neutral fluorine going to F plus. So in both cases, we have an IE1 of oxygen and an IE2 of oxygen and an IE2 and an IE1 of fluorine. Well, we know ionization energy 2s are going to be greater than ionization energy 1s because, again, we're taking it away from a positively charged ion, which is going to be harder than taking it away from a neutral atom. So we know it's going to be one of the 2s. But which one is it, oxygen or fluorine? If we look back to our trend, increasing first ionization energy, it's harder to take electrons away from fluorine than it is to take electrons away from oxygen. So taking in a second electron away from fluorine is going to be the absolute hardest, or it's going to require the most energy, as in this question, because it's a second ionization energy. Question 5 says, place the following in order of increasing radius. We have Ca2 plus, S2 minus, and Cl minus. So S2 minus is isoelectronic with argon, because it's got 2 extra electrons. Cl minus is isoelectronic with argon. And Ca2 plus with 2 extra electrons is also isoelectronic with argon. So all of these have their electron configuration of neon, 3s2, 3p6. And again, if you're not sure how to get the electron configurations, there's a video down below which goes over electron configurations in detail. So these all are isoelectronic, which means they have the same electron configuration. Well, what's the difference? Well, the difference is that calcium has 20 protons, sulfur has 16 protons, and chloride has 17 protons. I'm just reading their atomic numbers, respectively. The next thing we want to do is we want to think about what increasing radius means. Increasing means smallest first. I strongly recommend you do this so you don't get it backwards. Well, which one of these are going to be smaller? In this case, all of them are pulling on the same electron configuration, neon 3s2, 3p6, or argon, said another way. The one with the most protons is going to be the smallest. So Ca2 plus has the most protons. So it's going to be smaller than Cl minus, which has the next most protons, and smaller still than S2 minus, which has the least number of protons. Put simply, the more positive an ion is, the smaller it is. The more negative an ion is, the larger it is. Or you can think about it the other way that I just said. And in this case, the answer is choice letter C. Question 6 says, what period 3 element is described by the following ionization energies? And remember that ionization energy is the energy to remove one electron. So to remove the first electrons around 1,000, to move the seconds around 2,000, the thirds around 3,000, the fourth is around 5,000, the fifth is around 6,000, and then all of a sudden, to remove the sixth electron, it's around 22,000. So we're looking at a period 3 element, which means it has to be one of these here in period 3. Well, why is there such a gap between IE5 and IE6? Well, it's because these are valence electrons. It takes successively more because the ion is becoming more and more positive as you take away more electrons. But when you get rid of 5, now it's like a noble gas, or said another way, this is a core electron. This last electron takes so much more energy because now it's like taking an electron away from a noble gas, and or this is a core electron. It's just two ways of saying the same thing. So essentially what this is saying is, which period 3 element has 5 valence electrons? Well, remember the A group number tells you the valence electrons. So 1A has 1, 2A 2, 3A 3, 4A 4, all the way up to 8A with 8. So the period 3 element with 5 valence electrons is phosphorus, which is our answer. So we take 1 electron away, it's like silicon. 2, it's like aluminum. 3, it's like magnesium. 4, it's like sodium. 5, it's like neon. These are all a reasonable amount of energy. But then when we want to take away a sixth, it's a core electron. It's no longer a valence electron. Said another way, it's like taking an electron away from a noble gas, which is just extremely hard to do. And in this case, it's 22,000 to get to the next electron away. So that's how we solve that problem. Number 7 says, place the following in order of decreasing first ionization energy. So we have a trend on the periodic table here for increasing first ionization energy. And it's up and to the right like this. So helium has the highest first ionization energy, francium has the least first ionization energy. So now let's identify the location of the ions. So cesium is down here somewhere. Magnesium is roughly right here. And then argon is over here. It's a noble gas. It's in the same row, or the same period as magnesium, but it's all the way over on the noble gas side. So as we've done in several other examples, when it says decreasing, this means biggest first. So which one of these has the largest ionization energy? Well, the one that's closest to the top right corner. So argon is greater than magnesium is greater than cesium. So argon, magnesium, cesium is choice letter C. Question 8 says, which reaction below represents the electron affinity of lithium? Well, electron affinity is the opposite of ionization energy. So you can have, like ionization energies, you can have multiple of them. So EA1 is electron affinity 1. X in the gas phase plus an electron, and if you add an electron to X, you get X minus in the gas phase. EA2, electron affinity 2 for X, would be X minus, it already has an extra electron, plus an electron, yields X2 minus in the gas phase. So it essentially gets a second extra electron. You could repeat this until you put all the electrons in the universe onto X, which of course is not possible practically, but you get the idea. So you can have successive electron affinities. So we need to have lithium in the gas phase, and we need to add an electron to it, and we need to form lithium minus in the gas phase. This happens to be choice letter D. Lithium is a gas, plus an electron yields lithium minus in the gas phase. Lithium plus has nothing to do with it. If you add an electron to lithium, you don't get lithium plus, you get lithium minus. This is the ionization energy, not the electron affinity, and this doesn't make any sense because you already have lithium plus an electron yields lithium. So choice letter D is the correct choice here. Question 9 says, which of the following represent the Lewis structure for bromide, Br minus? Well, the dots in the Lewis structure are the valence electrons. So if we look, bromine's in 7A, so it has 7 valence electrons. Remember, the A group number tells you the number of valence electrons. 1A is 1, 2A is 2, 3A is 3, up to 8A, which is 8. 7A has 7, which means you would write bromine with 7 dots around it. However, because it's Br minus, we have an extra electron, which means we have to write 8 dots around bromine, which is 2, 4, 6, 8. In this case, bromide, Br minus, which is choice letter E. So the dots represent the valence electrons. If you have a charge, it's negative, you add extra electrons. If it's positive, you have less electrons, but in this case it's negative. So we didn't have 7, we had 8. Question 10 asks us for the reaction that represent the lattice energy of Li2O. So lattice energy is the ions in the gas phase forming a solid ionic compound. I'm just going to put forming a solid. So you have to have the ions in the gas phase condensing or forming a solid. So let's look at this. 2Li plus O2 minus yields Li2O solid. This looks like a correct answer. And if we look, oh, I apologize. This is Li plus aqueous plus O2 minus aqueous. These are not gas phase, so this is not the correct answer. Lithium solid plus O2 gas, these are not ions. Okay, so therefore this is not correct. Lithium solid yields 2Li plus O2 minus in the gas phase. This is the opposite of the lattice energy because we're destroying it. 2Li plus in the gas phase plus O2 minus in the gas phase yields Li2O solid. This is the correct answer. And here again we're destroying it and there's aqueous. So these answers are not correct for various reasons, because the ions are aqueous, because they're not ions at all, because it's decomposing as opposed to forming. The only one that here that gives you the ions in the gas phase forming the solid are 2Li plus O2 minus yields Li2O. Don't forget, as a reminder, 1A metals are plus 1, 2A are plus 2, 3A are plus 3, 5A are minus 3, 6A are minus 2, and 7A are minus 1. So you need to know the charges on the ions. So oxygen's in 6A, so it's 2 minus, lithium's in 1A, so it's plus 1. For number 11, it says place the following in order of decreasing magnitude of lattice energy. So decreasing means biggest first, and we've talked about that in several other examples. I strongly recommend you translate orders into biggest first or smallest first. So there are two factors that affect lattice energy. Lattice energy factors, if you will, things that affect the lattice energy. The first, the greater the charge difference, the greater the lattice energy. So what that means is if you have one ion that's plus 1 and one ion that's minus 1, that will have a smaller lattice energy than if you have one ion that's plus 2 and another ion that's minus 2. So the bigger the difference in the charge between the positively charged ion and the negatively charged ion, the greater the lattice energy. The second factor that you only consider if the charge difference is the same. So if the charge difference is the same, the smaller the ion, the greater the lattice energy. So, the first thing you need to do is identify the ion charges. To do that, we have to use the periodic table. So don't forget, 1A metals are plus 1, 2A are plus 2, 3A are plus 3, 5A are minus 3, 6A are minus 2, 7A are minus 1. Then we need to think about the size. Well, if they have the same charge difference, chances are they're in the same group. So as you go down the periodic table, the ions get larger. Or said another way, as you move up, they get smaller. So let's look at this example. So in this case, potassium is plus 1 because it's a 1A metal. Oxygen, or oxide, is minus 2 because it's a 6A nonmetal. So 6A is minus 2. Rubidium, plus 1. Sulfide, minus 2. Lithium, plus 1. Oxide, minus 2. So, in this case, the charge differences are all the same. They're all plus 1 and minus 2 for all of the ions. So if the charge difference is the same, the smaller the ion, the greater the lattice energy. Well, let's just look at the cation first, the positively charged ion. We have lithium, potassium, and rubidium. So lithium is going to be the smallest. So therefore, the smaller ion is going to have the greater lattice energy. Let's look at the nonmetal, the anion, oxide and sulfide. So oxide is smaller than sulfide. So lithium oxide is going to have the overall greatest lattice energy. So Li2O is greater than. What's next? Well, potassium is smaller than rubidium, and oxygen is smaller than sulfur. So potassium oxide is going to be the next smallest, followed by rubidium sulfide, which is going to be the largest. Note that we only considered the size of the atoms because there was no difference in charge. So this, when we do it all out, is choice letter C. Now let's look at a very similar problem. I'm going to kind of move this up as much as I can here. Just give me 1 second here. Fold the paper so I can move it up as high as I can. All right. So now it says which the compound below should have the highest melting point according to the ionic bonding model. And the thing that we need to remember is melting point is directly proportional to lattice energy. So melting point, and boiling point for that matter, is directly proportional to lattice energy. So essentially what they're asking us here is, which of the following has the highest lattice energy? Well, there's two factors that affect lattice energy: the charge difference and the size. So let's check the charges first and see if there's a difference in charges. And then if there isn't, if there's a tie, if you will, then we'll go for the size. So let's find our ions. So aluminum is in 3A, so it's plus 3. Nitrogen is in 5A, so it's minus 3. Rubidium is plus 1. Iodide is minus 1. 1A and 7A. So plus 1, minus 1. Calcium, 2A plus 2. Sulfide, 6A minus 2. Sodium, 1A plus 1. Fluoride, 7A minus 1. Magnesium, 2A plus 2. Oxide, 6A minus 2. So we want to find the one with the highest melting point, so the one with the strongest lattice energy. Therefore, we want the one with the greatest charge difference. Plus 3 and minus 3 are going to be more attracted than plus 1 and minus 1, or plus 2 and minus 2. So A will have not only the highest lattice energy, it will also have the highest melting point. It would also have the highest boiling point if that's what they asked for. So if you're looking for highest melting point or boiling point according to the ionic bonding model, what you're really looking for is lattice energy. Remembering that means you only have to learn one thing: lattice energy, and then you can apply it to two other things: melting point and boiling point. Question number 13 says, choose the best Lewis structure for CH2Cl2. And here I have a 4-step process for writing Lewis structures. Now, on the exam, you could be asked to write and interpret the Lewis structure of anything. So, down in the description below, there is about approximately 1-hour video where I go through in detail how to write the Lewis structure of pretty much any atom that you could, or molecule that you could think of. So I strongly recommend that if you're not sure how to do this, you watch that video. That being said, what I'm going to do here on the next bunch of questions is apply those rules, but I'm not going to go in them in great detail. So the rules are: count the valence electrons, put the least electronegative atom in the middle, except hydrogen. Your electronegativity trend is like this: increasing electronegativity. And I will say it doesn't always work, but it works most of the time. So fluorine is the most electronegative, followed by oxygen, and I explain more in detail what that is during the video. Fill the octets, except hydrogen. So hydrogen wants to be like helium, so it only has 2 electrons. 3A is use multiple bonds if you don't have enough electrons. So sometimes you might have to make a double or a triple bond. And root 3B is if you have too many electrons, expand the octets if you have too many electrons and the atom is period 3 or lower, which means period 3 or lower on the periodic table. So period 3, 4, 5, 6, 7, not periods 1 and 2 is essentially what that means. Then finally, minimize formal charges. And formal charges are something you can calculate mathematically, and that's shown sometimes. But if you watch the other video, I'll show you how to do the formal charges by counting, as opposed to basically having to do some kind of math formula. Okay, so that is basically that. So choose the best Lewis structure for CH2Cl2. So the first thing we want to do is count the valence electrons. Well, valence electrons are a group number. So if we look here, carbon's in 4A, so it has 4, plus, carbon's in 4A, so it has 4, hydrogen's in 1A, so it has 1, but there are 2 of them, so 2 times 1, 2 hydrogens with 1 valence electrons each, plus, chlorine's in 7A, and there are 2 of them, 2 times 7. Add them all up. 4 plus 2 is 6, plus 2 times 7 is 14, for a total of 20 electrons. 6 plus 14 gives us the 20 electrons. Now, we need to put the least electronegative atom in the middle except for hydrogen. So, increasing electronegativity this way. So carbon is less electronegative than chlorine. Hydrogen can't go in the middle. So, put the least electronegative atom in the middle, we put carbon in the middle, and now we have to bond it to all the things that are here. A hydrogen, a chlorine, and a chlorine. So we just bond it to what it tells us, 2 hydrogens and 2 chlorines. We have carbon in the middle. Now we need to fill the octets of the atoms. Well, if I look here, hydrogen doesn't want an octet, it wants 2, because that's helium-like, and hydrogen is very small. Carbon has an octet, 2, 4, 6, 8 total electrons around carbon. Note that there are 2 electrons in each one of these bonds. Then, chlorine does not have an octet. Well, I've used 2, 4, 6, 8 electrons. So now I want to start filling the electrons around chlorine. And I want to fill them in what are called lone pairs. So, lone pairs come in pairs. So, I have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I've now used 20 electrons, and I've also filled the octets of chlorine with lone pairs. Now I want to minimize formal charges. Now note that when you're doing step 4, it's important to learn this, and I strongly recommend the video if you're not sure how to do this. But essentially what we want to do is compare the number of electrons that something wants to have around it to the amount that it actually has around it. And although there are 2 electrons in this bond, formally one belongs to carbon and one belongs to chlorine. Said simply, count the dots as 1 and count the dashes as 1. So carbon is in 4A. It wants to have 4 electrons around them. Count the dashes as 1. It has 1, 2, 3, 4. Wants 4, has 4. It's neutral. I will note that minimize formal charge means try to make it 0. It does not mean make it as negative as possible. It means try to make it 0. So carbon is neutral. Wants 4 has 1, 2, 3, 4. Chlorine wants 7, it's in 7a, has 1, 2, 3, 4, 5, 6, 7. Count the dots as 1, count the dashes as 1. Something that has 7 electrons that wants 7 electrons is neutral. Hydrogen wants 1 and has 1. It's neutral. This is the best Lewis structure of, this is called dichloromethane or methylene chloride, and this is the best Lewis structure. I will note, and this is something important that I wanted to point out, that in this case, I put the chlorine here and here, and they put the chlorine here and here. It makes no difference. This is still the correct answer, even though the chlorines are not in the same order. Remember, you haven't gotten to this yet, but in three-dimensional space, it's not really either of these. So therefore, neither one is more correct. So I hope that was helpful, and I strongly recommend the Lewis structure video. In future questions, where we go over Lewis structures, I'm not going to spend a whole lot of time going through these rules. What I am going to do is suggest that you watch the video if you're not sure how to do them. Number 14 says, choose the best Lewis structure for nitrate, NO3-. So the first thing we want to do is count the valence electrons. And as it says in the description below, basically if you want to do Lewis structures, watch the video for number 13 first, which is going to refer you to the link below, which is like an hour-long video where I go through all of Lewis structures. So here I'm going to go over several examples. Okay, so if you're mostly there and you just want to go over a few examples, but if you're not sure how to do it, please watch the video, take notes during the video, and it will help you a lot. So the first thing is count the valence electrons. So nitrogen is 5a, so we have 5. Oxygen's in 6a, but there's 3 of them, so it's 3 times 6. And then it's negatively charged, so it has an extra electron, so we add 1 electron. So 5 plus 3 times 6 is 18, so 5 plus 18 is 23, plus 1 is 24 electrons. Now, we put the least electronegative atom in the middle. That is nitrogen. I'm going to bond nitrogen to 3 oxygens. Why? Because it's NO3. Now, I'm going to try to fill the octets. Well, one thing I notice is that 24 is evenly divisible by 8, so if I put 8 electrons around each oxygen, that'll be all 24 electrons. But if you're not sure, we have 2, 4, 6, 8, 10, 12. I've now filled the octet of that oxygen. 14, 16, 18. I've now filled the octet of that oxygen. 20, 22, 24. I have now filled the octet of that oxygen. I apologize, I had it off the screen there. So I put 8 electrons around each of these oxygens. But I have not successfully filled the octets. So I'm going to move this away. Alright, I'll refer back to it, but I'm going to move it away. Now notice, nitrogen doesn't have an octet. So notice what I don't do. I don't cross this out and start over. I decide I need to fix it. Well, how do I put more electrons around nitrogen if I don't have any more electrons? That is rule through AA. Use multiple bonds if you don't have enough electrons. So what I'm going to do is I'm going to take 2 electrons from this oxygen and put them there. And I end up with nitrogen double bonded to this oxygen, which now only has 2 lone pairs. This oxygen goes along for the ride, like this, and this oxygen just goes along for the ride, like this. Said another way, they're a single bond and 3 lone pairs. I have now filled all the octets. So now I can calculate and potentially minimize the formal charges. Well, let's start with this double bonded oxygen. Oxygen wants to have 6 electrons around it. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6. Remember, there's 2 electrons in each of these bonds, but we consider formally 1 belongs to nitrogen and 1 belongs to oxygen for both bonds. So 1 to nitrogen, 1 to oxygen, 2 to oxygen, 2 to nitrogen. Said another way, count the dots as 1, count the dashes as 1. So oxygen wants to have 6 electrons around it, and it has 1, 2, 3, 4, 5, 6. This one is neutral. Let's look at this oxygen with a single bond. Oxygen still wants to have 6 electrons around it. It's in 6a. How many does it have? 1, 2, 3, 4, 5, 6, 7. Oxygen has an extra electron. That makes it negatively charged. This oxygen is the same. It wants 6 and has 1, 2, 3, 4, 5, 6, 7. It's also negative. How about nitrogen? Well, nitrogen wants 5 and has, count the dots as 1, count the dashes as 1. There are no dots here, so 1, 2, 3, 4. It's missing an electron. Something that's missing an electron is positively charged. You will notice that negative, plus, and negative add up to overall -1. The sum of the formal charges has to add up to the charge on the species, in this case -1. So this, so far, looks good, but could we make it better? Could we make less formal charges? And you might be saying to yourself, yeah, just make another double bond. But you can't do that. And the reason is you cannot expand nitrogen's octet. Nitrogen is in period 2 of the periodic table. Only elements that are period 3 or lower on the periodic table can expand their octet. Nitrogen is not one of them. Therefore, this is the best Lewis structure. You'll note that this is choice letter E, and it's written slightly differently. They don't actually write the negative here and the negative here and the positive here. They just write it as overall -1, but it is the same Lewis structure. Note that it looks very similar to A, except in A, you have this extra lone pair on nitrogen. This doesn't have the right number of electrons, and therefore is not the correct answer. Question 15 asks us which bond below is the most polar, and then 16 is which bond below is the least polar. So, in order to answer this, we need to think about electronegativity. So remember that our trend here for increasing electronegativity is up and to the right, and it doesn't include the noble gases. So what this means is that fluorine, the most electronegative atom, likes electron density more than any other atom. So if it's in a covalent bond between two nonmetals, the electron density will spend more time around fluorine than it will around any other atom. So said another way, just because atoms share electron density in a covalent bond doesn't mean that they share those electron density equal. So the most polar bond is going to be the one that contains the greatest difference in electronegativity. So here we have H bonded to F. That's a very big difference in electronegativity. C bonded to H, those are about the same. Hydrogen has a similar electronegativity to carbon, although slightly less. H bonded to I is down here, so therefore it is less electronegative than H bonded to F, all right, or less polar because fluorine is more electronegative than iodine. H bonded to Cl, Cl is also less electronegative than fluorine, and H bonded to Br, Br is also less electronegative than fluorine. So the greatest difference in electronegativity is between H and F because F is the most electronegative atom. Note that carbon and hydrogen have a similar electronegativity, which makes this a pretty nonpolar bond, which comes up a lot in organic chemistry. For 16, we have to do the opposite. Choose the bond below that is the least polar, so the least difference in electronegativity. And we have the same exact idea. C bonded to Cl, C bonded to F, that's going to be more greater difference in electronegativity because fluorine's the most. C bonded to I, iodine is the least electronegative halogen, that's not man-made, and then C bonded to Br, which is here. So the difference between carbon and iodine is going to be the least, so this is going to be the least polar bond. C bonded F would be the most polar bond in this case. So this is how we can use electronegativity trends to look at the polarity of different bonds. Number 17 says, which of the following elements can form compounds with an expanded octet? So expanded octets can occur in period 3 or lower on the periodic table. Said another way, they can't be from period 1 or 2. Period 1 and 2 cannot form expanded octets. You can think about this as them not having d orbitals, but it's just a rule we have to remember. Period 3 or lower on the periodic table, so 3, 4, 5, 6, 7, can form expanded octets. So lithium in period 2 can't expand its octet. Carbon in period 2 can't expand its octet. Fluorine in period 2 can't expand its octet. Selenium, which is in period 4, can expand its octet, and therefore choice letter D is the correct answer here. Question 18 says, give the number of valence electrons in sulfate, SO42-. Well, sulfur's in 6A, so it has 6, plus oxygen is in 6A, and there are 4 of them, so 4 times 6. And then with the 2 minus charge, we have 2 additional electrons, so we have to add in 2 additional. So 6 plus 4 times 6, which is 24, is 30, plus 2 is 32 electrons. So remember, the A group number tells you the number of valence electrons, and if something is negatively charged, you add electrons. If something is positively charged, you would subtract electrons. But in this case, it's negative, so negative 2, so we added 2 additional electrons. Question 19. Sorry, I forgot to close that again. It says, draw the best Lewis structure for CO3 2 minus carbonate, including any valence resonance structures, and then it asks which of the following is true. So, when we're drawing Lewis structures, I strongly recommend that you watch the video below. And the video link below to Lewis structures will go over these 4 rules. I've done this in several other examples here, and in question 19, as well as in the other examples, I'm kind of just applying these rules, but I suggest you watch the video if you're not sure how to apply them to all of them, because maybe there won't be carbonate on your test. Maybe it'll be drawing the Lewis structure of something else. So, first step in the rules is we count the valence electrons. Well, carbon's in 4A, so it has 4, plus oxygen, there's 3 of them in 6A, so 3 times 6, plus 2 extra electrons because it's 2 minus. So when we do this, we get 4 plus 18, which is 22, plus 2 is 24 electrons. Now we put the least electronegative atom in the middle. Carbon is the least electronegative atom, so we put carbon in the middle, and we bond it to 3 oxygens because it's carbonate, CO3. So we bond it to 3 oxygens like so. Now, I have used 2, 4, 6 electrons. The other thing I notice is 24 is evenly divisible by 8. So if I put 3 lone pairs, or 8 total electrons around each oxygen, I will use 24 electrons. Counting by 8 can be helpful, but it's not necessary. So again, I've used 2, 4, 6, 8, 10, 12. I've now filled the octet of that oxygen. 14, 16, 18. I filled the octet of that oxygen. 20, 22, 24. I have now filled the octets of all of the oxygens. Now what do I need to do? Now I need to fill the octet of carbon. Well, rule 3A and the rules that I go over in that video is that we need to make multiple bonds if we don't have enough electrons. I can't simply just put another pair of electrons. So notice I'm fixing what I have. I'm not starting over. So I'm going to move these 2 electrons here. I have carbon double bonded to oxygen, like so. Bonded to oxygen. This one just goes along for the ride, so 1 bond and 3 lone pairs. And this one just goes along for the ride, so 1 bond and 3 lone pairs. So I just made this one look the same, and this one I took these 2 electrons and made them into a double bond. Now I want to minimize, or at least calculate, the formal charges. Let's look at this oxygen first. Oxygen wants to have 6 electrons around it. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5, 6. It's neutral. This oxygen, which is the same as this oxygen, still wants to have 6 electrons around it. It's still oxygen. What does it have? 1, 2, 3, 4, 5, 6, 7. It's got an extra electron. Something with an extra electron is negatively charged. The other oxygen is the same. It wants to have 6 electrons around it. It has 1, 2, 3, 4, 5, 6, 7. So this is negatively charged. What about carbon? Carbon wants to have 4 electrons around it. How many does it have? 1, 2, 3, 4. So carbon is neutral. So there's a big hint that I was going to have negative formal charges. It's carbonate, CO3 2 minus. So there's a negative charge on this oxygen and a negative charge on this oxygen. So therefore, I do have the 2 negative charges. Second of all, they're on my more electronegative atom, oxygen. Said another way, this is the best we can do. We weren't going to make all the formal charges 0 in the Lewis structure of carbonate. Now we just need to read the question or read the answers and figure it out. So it says in letter C, the carbonate ion contains 2 CO single bonds, and 1 C double bond. Oh, so we're good to go with choice letter C. So for the next 3 questions, we essentially have to draw the Lewis structures of BrO4 minus, NO2 minus, and SF4, and then answer questions about those Lewis structures. Now, there's a video linked in the description below that will go through a bunch of examples and give you details of how to draw the Lewis structures. However, for this particular question, these particular questions, what I'm going to do is just simply apply those rules. So the first thing we want to do is count the valence electrons. So bromine's in 7A, so it has 7, plus 4 oxygens in 6A, so 6 each, plus an additional electron because it's got a negative charge. So we have 24 plus 7, 31 plus 1 is 32 electrons. Now we want to put the least electronegative atom in the middle, which in this case is bromine, and we want to bind it to 4 oxygens because it's BrO4. Now, I noticed that 32 divided by 8 is 4, so if I put 8 electrons around each oxygen, that will give me the total of 32 electrons. Another way to do this is 2, 4, 6, 8, 10, 12, 14, that one's full, 16, 18, 20, that one's full, 22, 24, 26, that one's full, 28, 30, 32, that one's full. So now I've filled all the octets, because bromine already had an octet, and now I've filled all the octets of oxygen, and I've used the 32 electrons. Now I can calculate the formal charges. Well, let's look at these different bromines, or excuse me, these different oxygens. They're all the same. So they have 1, 2, 3, 4, 5, 6, 7 electrons around them, and oxygen wants to have 6 electrons around it. So we put a minus charge on each of the oxygens because they're all having an extra electron. They have 7 and they want 6. Count the dots as 1, count the dashes as 1. Well, bromine better be plus 3 or I didn't count my electrons right because it's overall minus. So if I have 4 minuses, I need a plus 3. Let's calculate it. Bromine wants 7 has 1, 2, 3, 4. It's missing 3 electrons, so sure enough, it is plus 3. When you see a formal charge of plus 3, there's something wrong. So now what we need to do is look at how we can minimize this formal charge. Well, in this case, we need to add more electrons around bromine. Well, what has extra electrons? The oxygens. How many extra electrons do we want to add? 1, 2, 3. We want to make 3 double bonds. So if we have bromine double bonded to oxygen, double bonded to oxygen, double bonded to oxygen, and then single bonded to oxygen, and this oxygen has a negative charge. Bromine is in period 3 or lower, so it can expand its octet. Bromine's here in period 4, so it can expand its octet. So this is a much better Lewis structure than the original one, because we don't have a plus 3 formal charge. We just have 1 minus charge, and we have it on the more electronegative atom, oxygen. This means that bromine has a formal charge of 0. Note that we drew a Lewis structure based on the rules. Right, here are the rules again, and I strongly recommend that you watch the video if you're not sure about these rules. But then we fixed it. We didn't cross this out and start over. Let's do another example. NO2 minus. Here we have 5 plus 2 times 6 plus 1 extra because it's negative. So we have 2 times 6 is 12, 17, 18 electrons. Put the least electronegative atom in the middle, nitrogen, and bond it to your 2 oxygens. I'm now going to fill the octet of both of the oxygens, and that'll be 16 electrons because 2 8s are 16. I then have 2 more electrons because I have 18 total electrons. So what atom doesn't have an octet? Nitrogen. So I'm going to put them on nitrogen. I'll notice that nitrogen still doesn't have an octet. Well, if I don't have enough electrons to give a nitrogen an octet, consider a multiple bond. So I'm going to move those in there. So I get nitrogen double bonded to oxygen, which has 2 lone pairs, and bonded to single bonded to an oxygen, which has 3 lone pairs, and that lone pair on nitrogen comes along for the ride. Now let's calculate formal charges. The formal charge on this oxygen, it wants 6, count the dots as 1, count the dashes as 1, and it has 1, 2, 3, 4, 5, 6. It's neutral. How about this oxygen? Wants 6 has 1, 2, 3, 4, 5, 6, 7. we found our negative charge, and it's on the least electronegative atom. Note, the overall charge is minus, so one of the atoms has to have a formal charge of negative. Now let's look at nitrogen. Nitrogen wants 5, has 1, 2, 3, 4, 5. Wants 5, has 5. It's neutral. To answer the question, the formal charge on nitrogen is 0. Finally, how many lone pairs are on S in SF4? So here we have 6 plus 4 times 7. So 6 sulfur is in 6A, so it has 6 valence electrons. Fluorine's in 7A, so it has 7, and there are 4 of them, so we have to multiply by 4. And that gives you 4 sevens is 28, plus 6 is 34 electrons. Put the least electronegative atom in the middle, in this case sulfur, and bond it to 4 fluorines, like so. I've used 8 electrons. I can count out all the electrons, or I'm just going to put 8 electrons around each fluorine. If I put 8 electrons around 4 fluorines, that is 32 electrons, because 4 times 8 is 32, and counting by 8 can be very helpful in Lewis structures because it's less counting. So now I've used 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. So now I have 4 more electrons. Well, where am I going to put them? There's only one atom in the system that's period 3 or lower. Sulfur's in period 3. Fluorine's in period 2. So sulfur can expand its octet, but fluorine can't. So I'm going to put those extra electrons around sulfur. How do I check to see if that's a good idea? Formal charge. Let's look at fluorine. Fluorine wants 7, has 1, 2, 3, 4, 5, 6, 7. Remember, count the dots as 1, count the dashes as 1. So if it wants 7 and it has 7, it is neutral. Sulfur wants 6 and has 1, 2, 3, 4, 5, 6. It is also neutral. To answer the question, how many lone pairs of electrons are on sulfur? The answer is 1 lone pair. So drawing the Lewis structures allows us to answer questions 20 through 22. Remember, there's a video linked in the description below that goes over how to do this for pretty much all the molecules, not just the examples found on this sheet. So I hope you found this video helpful, and it helps you prepare for the next exam. But these are just some questions from chapters 7 and 8.